Thank you and welcome also, sir.
Just yeah, you pressed from your side for the recording.
Yes, sir, I press that.
Yeah, no problem. I thought it came from my side. No problem. Yeah.
Okay, thank you very much, sir. So, with the formal welcoming on the third day of the SFTP, on behalf of Shri Vishkarma Skill University, Palwal, Haryana, I, Dr. Preeti, co-coordinator, and Dr. Sanjay Singh Rathore, sir, coordinator of the 6 days AICT Atal Faculty Development Program on driving the future sustainable mobility through electric vehicle technologies and MATLAB simulations, are delighted to welcome all of you to this third day of the FTP. Today's expert talk on the highly significant and the futuristic theme, that is dynamic power allocation for fast charging of diverse electric vehicle fleets. As the world transitions towards the sustainable mobility, the need for intelligent charging infrastructure and optimized power management has become more critical than ever. So today's session will bring valuable insights into these emerging challenges and solutions. It's an honor and privilege to welcome Professor Mohan Kole, an internationally renowned academician and researcher with over 25 years of experience in the fields of smart energy systems, electric mobility, and renewable power technologies. Professor Kole, sir, is currently serving as Professor, Faculty of Engineering and Science at the University of Agder, Norway. He is globally recognized for his significant contribution to energy systems optimization, power distribution, smart grid planning, EV charging infrastructure, and sustainable electricity technologies. He has led numerous high impact international research projects, published extensively in top tier journals, and continues to be a leading voice in shaping the future of sustainable energy. We are truly fortunate, sir, to have you with us today to share your expert perspectives in this particular domain. We heartily welcome you, sir, on this particular platform, and I hope the participants will be benefited from your expertise. Session is over to you, sir.
Thank you, Dr. Preeti, for introducing me and giving some background about my work. I'm very privileged to join this AICT Atal sponsored 6 days faculty development program, which is focusing on sustainable mobility through electric vehicle technologies. This is a very interesting topic. Uh, can you, Preeti, can you able to see my slide?
Yes, sir, it's visible, sir.
Yeah, and then if I move to next slide is changing.
No, sir, no, it is not
Yeah,
changing. Only the first slide is there.
and now
Not,
no.
sir. No.
Okay, don't worry. Yeah, now I got the control. Yeah. So the
Yes.
topic is very interesting, and we know that we have to move towards the sustainable mobility. To move towards the sustainable ability, mobility, we can contribute in many ways. As all of us aware that Indian government has agreed to be net zero by 2070, and we know that due to present environmental conditions and pressure to move towards the net zero system, sustainable mobility in which electric vehicles are going to play major. Electric vehicles, they are very important for our sustainability, to have clean environment, to have our better health also. But when we are having huge number of penetration of electric vehicles, we are going to face lot of technical operational challenges also. To overcome those operational and technical challenges, we need to work on developing appropriate infrastructure for providing clean electricity to the diverse electric vehicle fleets. That is going to be a big challenge. We know that within our distribution network, we have limited resources. We have the limitation of our distributed network capacity. Due to that, providing resources or providing charging resources to upcoming electric vehicles are going to become very challenging. So in today's lecture, we would like to cover that, how we have to do the coordination of diversified electric vehicles at the fast charging station to dynamic power allocation, considering the user priorities also. Briefly, I have provided you the background, but we need to have some motivation on doing such type of work in which we are going to do the charging management of diversified electric fleets at a fast charging station. To do that one, we have to consider how we can design fast charging station by taking into account the available local resources, distributed generations, and of course, taking into account the expected increase in electric vehicle penetration and considering the traffic distribution, we need to select appropriate location of fast charging stations. But when we are trying to find out appropriate EV charging station, fast EV charging station, we have to consider some international standards also. Using those international standards of the charging, we may need to develop the architecture of fast charging station, and whether that architecture it is going to be based on DC microgrid or AC microgrid depends on the location and depends on the upcoming technologies also, or how we are integrating other renewable energy sources there. And then when we are having this fast charging station, we need to do some analysis how they are going to operate with reference to the diversified users and how we can use charging coordination among the electric vehicles which are connected at the electric vehicle fast charging station by considering the user preferences as well as the network constraints. And then I'm going to provide you the conclusion. So overall, I have provided you the high level overview of my lecture, and this information, what we will get from this lecture is going to be very useful, not only from the academic point of view also, but also in designing, developing, operating, and managing electric vehicle fast charging station, considering local geographical situation as well as the local traffic conditions also. So overall, this lecture is going to be useful for energy planners also, for the people who are working on designing sustainable transport network. They may get benefit out of that also. And of course, when we are talking about the fast charging station, considering the diversified electric vehicle users, so there is a business opportunity also. So that is also very interesting. So I believe that most of the participants who are here may be from the academic organization, so they can utilize some of the learning from this course for improving their teaching, or maybe when they are giving some industry lectures related to this topic, they can provide the information and the industry people can also get benefited. So it is more like train the trainers. So let's say you people are in the academics and I'm training you or I'm providing some of the learning from my projects to you, and maybe then you can utilize them for further transferring to the other stakeholders. Now, why we need to work on fast charging station? I have taken this statistics from International Energy Agency. If we use the as it is scenario, that is called steps scenario. In the steps scenario, you can see that by 2030, as per International Energy Agency statistics, we are going to get, let's say, around 140 million vehicles. Out of that, most of the majority is going to come passenger battery electric vehicles, and some portion it will be for plug-in hybrid electric vehicles, and some for the commercial also, and commercial public transport also. But what we have seen that most of the countries, they agreed to have that net zero target. Most of the developed countries, they feel that by 2050 they will be in a position to achieve the net zero target. Similarly, India has signed the agreement by 2070 want to become the net zero, and of course by 2030 we have to increase the renewable shares by 3 times. So by considering all this factor into account, if we take the sustainable development scenarios, then by 2030, around 240 million electric vehicles will be there on the road. Now, considering this huge demand, right, then how much electricity will be required? So if we take the steps scenario as it is scenario, then by 2030, with reference to the 2019, around 5 times increase of electricity demand will be there, especially for the electric vehicles. But if we take the sustainable development scenario into account, then by 2030, around 1000 gigawatt hour electricity will be required. And here we can see that most of the requirement is going to be for light duty vehicles. It means that we need to develop the fast charging station to supply the electricity or to fulfill the demand of this upcoming electric vehicles in a systematic manner to get them charged very fast. So now here you got the background that why we need to work on developing fast charging station. By moving to the next slide, you can see that there are different architectures for the vehicles based on their propulsion system. We are aware about internal combustion engine vehicles. We are aware about plug-in hybrid electric vehicles also. Somewhere we have hybrid electric vehicles also. We may have in future fuel cell electric vehicles and fuel cell hybrid electric vehicles also. But taking into account the scenarios of electric vehicles, which we have seen in the previous slide. Here we can see that mainly the battery electric vehicles and then some portion of the plug-in hybrid electric vehicles will be there. In today's lecture, we will try to focus that how we have to fulfill the charge of these battery electric vehicles. Now, some of you may be aware that there are different type of vehicle models. They are commercially available from leading manufacturers of automotive sector, and depending on the market requirement and development of the batteries, different capacities are there, and most of the leading manufacturer, they are moving towards to have very high capacity batteries, to have the higher autonomy range. Now here, I will take the example of Tesla Model Y. Tesla Model Y is having the capacity of 465 kilowatt battery electric vehicles, and its battery is of 100 kilowatt hour. I have driven Tesla Model Y couple of times. It has the battery voltage 350, and in idle conditions, if we consider the European driving patterns, it can go up to, let's say, 500 kilometers. But depending on the climatic conditions, depending on environmental factors also, this autonomy of 480 kilometers may reduce also. Now here you can see that this Model Y, in which battery is having 100 kilowatt hour and it has the autonomy range of 480 kilometers. So if we want to charge that at the fast charging station, so you can see that how much demand is going to be there. Now here, let's say if we consider the BMW. Now this information is little bit old now. This BMW i3 model, now no more BMW is manufacturing that one. Now BMW is moving towards very high autonomy vehicles, maybe around 500 kilometers. So it means that the huge demand is going to be there, and that to fulfill that demand, we need to have fast charging station. So to have that fast charging station, there are different type of chargers are available. But in most of the cases, now DC fast charging units are going to be implemented. This AC level 1, level 2 charger, mainly they are used in domestic connection, but these fast charging stations, they are going to be used at commercial level at the fast charging station. So if we do some analysis between the relationship of daily distance traveled and the number of daily fast charging events that have been given in figure 5. We will not go in much detail about that one, but we will try to give much more focus on EV charging stage, or how we have to develop the EV charging station. We have seen that most of the leading car manufacturers, they are manufacturing the battery electric vehicles of very high capacity. Let's say now the fashion or most of them are manufacturing of around 100 kilowatt hour battery capacity. And if we take the 100 kilowatt hour battery capacity, then its rating may be around 465 or something, 500 kilowatt in that range. Now, considering all those factors into account, okay, we are not allowed to make any changes within the electric vehicles. But considering the local situation into account, available local energy resources, we may need to manage the charging stage. Okay, so how we have to work on charging stage, because most of the car manufacturer, they are not allowing us to do any modification on stage 2 and stage 3, let's say, and we have to consider this electric vehicle, right, as a one unit, as a load, right, and taking local resources condition, local energy economics, local grid constants, we have to work on charging stage. In charging stage, there are some international standards also, and these international standards we may need to apply in developing this fast charging station within India also. So there may be some standards or the protocols for communications, connections, and the cables which we are using, which type of chargers we are using, so on and so forth. Now, some of the countries, they have their own standards also. For example, Japan, China, Taiwan. But I believe that in most of the cases, we may go to the international IC standards. Considering international IC standards, if we have to develop the fast charging stations, so here you can see that one fast charging unit, let's say if I consider CCS type 2, which is very widely used within the Europe and even in Norway also, it has the maximum power of 350 kilowatt. Now I have seen, now in place of 350, it is 400 kilowatt also. And those CCS type 2 charger are commercially deployed at the fast charging station. One charging pool or one charging unit, let's say it is having CCS type 2, having the capacity of, let's say, 350 kilowatt, and if we are putting 10 chargers there, so these 10 chargers are going to create around 3.5 megawatt demand on one fast charging station, which is a huge demand. So we have to consider, let's say if we are going to put the 10 charging pool at one charging station, let's say of 350 kilowatt each, to 3.5 megawatt demand within the distribution network, will our distribution network is going to have that facility or capacity to supply this load? I doubt, because our distribution network is not designed for that much capacity. And considering the Indian condition, where we have the huge demand of vehicles, right? So there will be, at a fast charging station, 10 charging pools may not be able to fulfill this upcoming demand of electric vehicles. Then you can see that another one, Chaochi, which is going to have the combination of CHAdeMO and GPT, and it has been said that it is going to have the capacity of 900 kilowatt. So still this has not been commercialized yet, but CCS type 2 and Tesla, they are commercially available here. Okay, so now if we are using these international standards and putting, let's say, CCS type 2 for fast charging station, then we have to see that how we can provide the demand for these CCS type 2 connectors at fast charging station. So for that one, we need to work on developing fast charging station. So let's say if I take, Tesla Model 3, and if I take its range of 450 kilometer and charging power available, let's say 250 kilowatt. So to charge average charging power from state of charge 20% to state of charge 80% in 15 minutes, we are going to require for Tesla Model 3 within that 50 minutes 250 kilowatt demand. You see, and the charging power 174 kilowatt average. So you say within that 15 minutes. So within that 15 minutes, 174 kilowatt, we can calculate how much energy is going to be required there, right? How within that short period of time to charge the battery of Tesla Model 3 from 20% to 80% in 15 minutes, how much demand is going to be there. So that demand we need to manage. And how we should manage it, that we are going to discuss in today's lecture. Let's say if we take rather than full autonomy or maybe from 20% to 80%, let's say we want to charge our vehicle for 200 kilometer, and if we are doing with Tesla supercharger in which capacity is 140 kilowatt, not the 250 kilowatt, okay, then it is going to take 13 minutes. But if you use the fast charging of 400 kilowatt capacity, what we discussed earlier, and then you can see that for 200 kilometer, the time which is required to charge is 5 minutes. So time is important here. So considering all these factors into account, we need to work on developing fast charging station. So how we have to work on that one? So to get that one, we need to work on developing fast charging station and its appropriate architecture. In some condition, we may use AC microgrid architecture, and in some condition, we may use DC microgrid architecture. So here in figure 6a, you can see that if we are using AC microgrid architecture, then at each charging point, we need to have additional AC to DC unit in addition to DC-DC converter. But if we use DC microgrid architecture, then we can eliminate that AC to DC converter which are required for each charging pole, and that we can make it integrated with a transformer, okay, and then it will be quite easy for us to integrate directly the energy storage also, as well as some distribution network also. So it all depends on which type of architecture which we are going to utilize and how our distribution network is going to help on that one. Then if we go, let's say, on AC microgrid architecture, so within the AC microgrid architecture, there may be possibility, right, to have much more integration by using some of the Drupe functionality of active power versus frequency, Drupe power, characteristics of the reactive power and voltages. And if we implement that for managing the power flow between the different charging units, then there is a possibility also we can integrate distributed energy storage on each charging unit in addition to the centralized energy storage. So here you can see that when we are talking about the fast charging station, and with fast charging station we are talking about the megawatt level demand. So that megawatt level demand, to manage, first we need to select appropriate architecture. In one of my work in which we highlighted DC microgrid architecture for fast charging station, and in which we included hydropower plant, distributed hydropower plant coupled with permanent magnet synchronous generator and directly linked to the DC bus, and with reference to the voltage sustainability on the DC bus, the input fluid flow of the hydropower plant, which have been integrated on the DC bus, that have been managed with reference to the dynamics of the EV charge. So, with reference to that point, two of my PhD students, in cooperation with VNIT Nagpur, they did a wonderful work on developing DC microgrid fast charging station, right, for managing the dynamic demand of the electric vehicles by integrating hydropower plant within that microgrid and reducing the demand on the main grid and to fulfilling the local demand, right? So here the point is that such type of architecture and such type of integration of distributed generations are going to depend considering the local network constraints as well as local resources available and local traffic pattern. It means that there is a scope for doing further research work with more focus on the from the field point of view for a particular location. Okay, and of course, in most of the cases, we may not be allowed to do any altercation within the electric vehicles, but by considering the local condition, we may be in a position to do the charging management locally by making it more sustainability of power supply to the diversified electric vehicles, considering the grid constraints and integrating the distributed generator on this either DC bus or AC bus, considering any of the architecture which we are going to select. So I have given you briefly about the architecture in which we are integrating battery energy storage also, and depends like whether we are using solid state transformer and so on and so forth. And we will not go in much more detail, but here the one word is there, that is varying bus voltage. This varying bus voltage, it means that to maintain the voltage sustainability on the DC bus is going to be very important for distribution of the load for distribution of the load uh, within these electric vehicles as per the diversified demand. Okay, so if you are interested on this topic and to understand that DC microgrid architecture and the operation of distributed generator with example of hydropower plant, so I request you to refer my published articles, and most of them they are open essays also, in which all detailed mathematical modeling of dynamics of the electric vehicles, dynamics of the batteries, and how we have to maintain the sustainability of the voltage on the DC bus, and then how we have to manage or how we have to integrate hydropower plant, for example, and then by using this bus voltage signal, right, how we have to control the input fluid flow to the turbine, that have been explained in a very systematic manner, which you people can utilize in your teaching also, or maybe in your research work, or maybe you can disseminate those findings to the industry or the energy planners also who are working on developing fast charging station by taking into account local resources. Now, moving forward, one of the work which I did long back related to the hydrogen also. We have seen earlier that hydrogen-based vehicles may come into the future, and we have seen that in some countries already they are demonstrating hydrogen-based public transport in a very systematic manner. So with objective that to reduce the CO2 emission and to utilize the green hydrogen produced by using renewable energy sources. I did a lot of work on that one, but in today's lecture, I'm not going to discuss about that one. Now we are coming to the key point, and that key point is how we have to develop, deploy, and do the operation management of fast charging station. And this deployment, development, maybe design, development, deployment, and operation management is going to be based on local conditions. So this is not going to be the universal solution. For making this one, we need to consider local situation into account. So one of my PhD student, he did work on this one. So his objective was that if we have the fast charging station, and within that fast charging station, when we have the electric vehicles there, so how we have to fulfill their charging demand, okay, and not only fulfilling their charging demand, but taking into account the user satisfaction also, and how the diversified user, considering primary user, secondary users, or opportunistic user, how we have to manage their demand. So I will explain this figure 10 in a very systematic manner so that you will be in a position to understand how we have to design, develop, and deploy the fast charging station and how we have to work on its sustainable operation for fulfilling the demand of diversified electric vehicles. Let's say here we have the fast charging station. This fast charging station, in this situation, let's say it is connected to the distributed system, and distributed system network is going to have its own limitations also. And of course, we know that this fast charging station is going to have very dynamic demand as per the expected arrivals of the electric vehicles. Let's say some electric vehicles are there within that fast charging station. And as we have seen previously, that every electric vehicle is going to have different capacity, different charging demand, depends on their driving patterns also and the requirement also. Based on that, those electric vehicles which are connected at that fast charging station, they may say that yes, within that particular time period, based on their requirement, they can make the charging request this fast charging station. But that fast charging station operator has to decide that at that particular time, how much capacity is available. So depending on how many number of electric vehicles are there and depending on their demand, so these electric vehicles are going to make a demand to this fast charging station operator. Okay, so based on that, this fast charging station operator has to fulfill their demand, but of course, taking into account the grid constants. Based on that, then charging station operator, fast charging station operator can make certain demand to the DSO. So this DSO, depending on other loads available there at that during that particular time or the duration, may say that I can provide you up to a certain demand also, not your fulfilled, not your the completed demand. So let's say this DSO said that during this particular 15 minutes of time, for example, maximum charging capacity which can be provided. So based on this maximum charging capacity which is available at this fast charging station operator, now this fast charging station operator has a duty to communicate these electric vehicles which are connected within that fast charging station within that particular time period, how much charging capacity is going to be available. And of course, the different users may have different demand requirement. So accordingly, that distribution can be done automatically by that fast charging station operator. So here you can see that if we want to develop the algorithm based on the user preference, based on the user requirements, taking into account the DSO constants, which is going to be the dynamic, how we have to dynamically manage the charging demand of electric vehicles within the fast charging station. So that is going to be a very challenging. So that has been the key point of today's lecture. Is it okay? Are you able to follow now? So this is a very interesting point, and it may create a lot of questions in your mind also. And this is not only the academic research, but it is a industry or utility based research, right? And it is our duty from the academics point of view, like how we can contribute in that work in which we can develop some algorithms for operation of the fast charging station, and how those algorithms or how this work can be implemented into the field for making more satisfaction of the electric vehicles by getting them charged as fast as they can based on their travel demand. What I have seen in most of the research work, especially from the academic research work, the focus has been very lower capacity of charging units. So these lower capacity charging units take hours and hours to charge the electric vehicles. And we have seen that now the capacity of the electric batteries within the electric vehicles are increasing. And everybody wants to get their unit charged very fast. So those slow chargers or the slow charger which may be connected at the home may not be in a position to fulfill the expected exponentially increasing electric vehicles demand, for which we need to design, deploy the fast charging station, and for that we need to have operation mechanism management. Now, coming out of this fast charging station, we have to consider the traffic network also. So this traffic network is very important, as we have seen that due to the advancement of the technologies, most of the vehicles, they are integrated with the navigation platform, and this navigation platform can help the users to identify the nearest fast charging stations also, in which they can observe that how much capacity is going to be available at that fast charging station, so where the user can go and charge. Considering this navigation platform, and let's say some electric vehicles which are within the traffic network and they are moving, and of course based on their travel demand there will be some charging requirements also, considering their reserve also. So that information they can communicate through this navigation platform regarding their charging requirements. Okay, and that charging requirement through this navigation platform can be communicated to this nearest or the fast charging station operator which is available within that traffic network. But now this fast charging station has to consider that how many electric vehicles with diversified demands they are connected, and when their demand is going to be fulfilled, how much the capacity available, right? And then of course nothing is free. It has to say that yes, I have the availability of the resources, charging resources, but I'm going to charge you at this particular price. So dynamics of the pricing are also going to be there. So now that information is going to be communicated through this navigation platform to the electric vehicles which are outside of the fast charging station. Yes, I can make the demand available to you during this particular time period, but at this particular price also. Now here you see this demand is again dynamic, this is again dynamic, this is again dynamic, and of course this fast charging station has to make the profit also, and of course the market competition is going to be there. So then this fast charging station operator has to design some charging pricing mechanism also that is going to be very dynamic also to fulfill the expected demand of the electric vehicles. Then only we will be in a position, to have higher penetration of electric vehicles, because the users are satisfied with the fast charging as well as considering the dynamics of the energy pricing also. So now here you can see that yes, of course, it is important from the government policy point of view also, like we want to reduce the CO2 emission to have more electric vehicles, but we need to have active participation from the users. So active participation from the users will come if they see that their demand is fulfilled within a specified time, within the particular pricing range, then only the users will purchase the electric vehicle. So this slide is very interesting and very important in making the planning for fast charging station design, deployment, and operation mechanism management. In this slide, some of my students, they did the work on fast charging station operation management with reference to the electric vehicles which are connected within the station, right, as per their demand, taking into account their preference. But we have not covered at this work. So if suppose some potential researcher interested in working on this work, so I am very open to help them to work together in developing some mechanism, right, for the electric vehicles which are outside of the fast charging station, taking into account the dynamic resource constraints of fast charging station, as well as developing some pricing mechanism also. Is it okay? Are you able to follow?
Yes, sir.
If anybody is having any questions, we will take the question at the end. Okay. Now moving forward, we have seen the positive impact. Okay. Positive impact is very interesting. Okay. But we have a lot of technical operational challenges. Long charging time, if you are using slow charger, everybody want to have the fast and to have higher range also, more autonomy also. But considering all these factors, we need to work on fast charging and deploying those charging stations. But those fast charging stations are going to create a lot of impact on the distribution network. So we know that we have the limited capacity of the distribution network. And of course, the further integration of electric vehicles due to the increasing demand, it is going to impact the electricity market also. There may be chances due to that, the domestic electrical energy pricing, what we are going to get, it may get increased also. Okay, so that factors also we need to take into account. Then we have to consider within that distributed network, due to this expected dynamic demand of electric vehicles, whether our local network is going to be operating under the stable condition or not, and how it is going to impact the power quality also. So those factors also we need to study. Now I'm going to give you some results from my work in which the motivation is that how or why we need to do the charging coordination. If we go back on this slide, so here we have the electric vehicles which are connected at the fast charging station. So here what I mentioned that we are going to have diversified electric vehicles. So these diversified electric vehicles are going to have very diversified demand, and of course some of them will be the opportunistic users also, right? Some of them may be the primary users also, and then we have the dynamics of the charging capacity. So why we need to do the coordination here within this electric vehicles, that is explained through this result. Okay, and reference has been given here. If you are interested to understand all its technical details, including mathematical modeling, you can refer that one also. So let's say in figure 13, we have 24 hours time. Within this 24 hours time, let's say on that fast charging station, electric vehicles are coming and getting charged, let's say in a random manner, because we never know when the vehicles will come. And of course, again, it depends on the traffic patterns also, and that also we need to do some analysis on that one also. So let's say if users are coming and getting connected to this fast charging units, okay, the load demand is like this. Okay, that is, let's say, uncoordinated charge. But in that slide, we have seen that the demand limit, but that fast charging station is going to be dynamic, because distributed system operator has to see that how much demand is available at that during that particular time, giving the priority to other loads also, and of course taking into account the network limitations also. Let's say, considering those factors, the demand limit is imposed on the fast charging station operator. So fast charging station operator has the duty, right, not to exceed this demand limit, but manage the charging of the connected electric vehicles, right, either using adaptive approach or maybe fixed rate charging to not to exceed these dynamic demand limit. Okay, now considering this adaptive, let's say we will work on the fixed rate charging. So in the fixed rate charging, we can see that how the demand have been fulfilled. But if we use the adaptive charging, in adaptive charging, we can increase the supply to that electric vehicles, of course taking the constants here, and we can satisfy their demand little earlier time compared to the fixed rate charge. So the results are explained in this figure, and more details about the results are available in reference 4. But how this fixed rate and adaptive charging is going to help? Now, if we use adaptive charging, it means that the users will get their requirement fulfilled as fast as they can, and then it is going to create more opportunity for coming new vehicles for getting it charged. It means that the blocking probability is going to be reduced if we are going to use adaptive charging with reference to the arrival rate of vehicles at that fast charging station. With reference to the arrival rate of fast charging station, and if we use the adaptive charging, then you can see that how the blocking probability of the vehicles which are going to arrive at the fast charging station is reduced compared to the fixed rate charging. So here you got the idea how we have to do the charging resources coordination. How we have to do the charging resources coordination, right? Considering the demand limit, either using the adaptive charging and fixed rate charging, and how that is going to be the beneficial for understanding the blocking probability with reference to the arrival of the fast charging station. So one of my PhD student, his name is Sandun Konara, he did this work, and this work have been highly appreciated by many industries, many utilities, and many fast charging station operators also. Now, we got the idea now. Why we need to have fast charging station? Then why we need to have the coordination also? So now question comes to do the deployment and the coordination appropriately. So the first thing is optimum siting and size. So when we are talking about fast charging station, doing the coordination, right, we have to consider that how we can do or how we can utilize the or how we can make the maximization of the profit of fast charging station or aggregated fast charging stations, okay, and of course taking into account the minimizing the impact on the power grid and energy market also, and of course we have to provide the quality service to the electric vehicles. So for that, first thing is that we have to find out the optimum siting and size also, depending on the traffic patterns and available local resources, and taking into account the international charging standards, like whether we are going for the 400 kilowatt pool or what, we need to design, or we need to first find out the sizing and the location of the fast charging station. And for that fast charging station, we need to consider the local traffic patterns, local road network, and based on that, we have to find out which location is going to be useful, how the cost is going to be there, quality aspects, grid stability aspects also. And for doing that, there are some typical techniques we can use, let's say optimization models or graph theory based models or queuing theory based models for that purpose. But first, let's say forget about the techniques, but main objective is how we have to find the sizing and siting of the fast charging station. Then next is that for that fast charging station, how we are going to develop architecture also, whether we are going to use AC microgrid architecture or whether we are going to use DC microgrid architecture. And of course, for that architecture and sizing, we need to consider not only the technical but the economic parameters also. Now, coming to the charging resources management for that fast charging station, let's say, which we have designed and deployed. So here we classified the electric vehicles in two categories. One is scheduled electric vehicles and another one real-time opportunistic electric vehicle users. Scheduled electric vehicles, we may say the primary users, and those primary users may have some contract with this fast charging station. Of course, some pricing mechanism is there that they always want to fulfill their demand whenever they arrive. Some of them secondary users. So secondary user, we can say that opportunistic user. They can come at any time, and depending on the available resources at that charging station, they can fulfill their demand. So if we consider the arrival rate of primary users, arrival rate of the secondary users, and depending on the charging station availability, which type of users they have been connected there, how the users after fulfilling going back, and some of them, maybe the secondary or opportunistic user, may have to leave this charging station if the primary user is coming. So then they are going to be the preempted electric vehicles also. So all these factors we need to consider in doing the coordination with objective that in minimizing the blocking of or minimizing the blocking probability of arrivals of electric vehicles at that charging station, but giving the priority to the primary users because they have that agreement. Considering all these factors into account, we may need to have some hierarchical control architecture also. So that hierarchical control architecture and coordination, we need to use some control aspects. Within that control aspects, we need to consider economic aspects also. And economic aspects is maximizing the EV aggregation or the fast charging station profit. And of course, minimizing the charging cost. Then of course, we need to consider operational and technical aspects also. Within that, we have to basically utilize resources in a very systematic manner. Okay, we have to reduce the waiting time, and we have to consider the frequency or the pattern of the vehicles which are arriving and accordingly adjusting the resources also and reducing the charging time, providing the good quality service, but at the same time contribution towards the grid stability. So for that, the timing aspects are very important, right? Because we are going to do the dynamic charging management or the scheduling also. So in some condition, it may be the offline strategy, but in most of the cases, it is going to be the online strategy. So here, when we are talking about the online strategy, it means that then we are integrating information communication technology infrastructure within this fast charging station. When we are talking about charging strategies and online strategies, we have to consider in a systematic manner different uncertainties which are going to impact this operation. So impact the operation of charging process. So energy price uncertainty is going to be there because the demand is there, supply is limited. So pricing volatility will be there. Demand uncertainty is there. Power supply uncertainty is there. Utility constraints are there. EV mobility variations are there. And of course, we need to consider system failure also because some of the components may get failed also. So that reliability factors also. So there are a lot of uncertainty aspects which we need to understand and solve. So for that, we can use different techniques, for example, optimization techniques, heuristic algorithms, or Q-based algorithms also. But for these techniques, the main input which may need is energy pricing, where we need to have the forecasting and the real time also. Similarly with the power and energy, EV mobility, utility constraints, grid constraints, battery constraints, and the user preferences also. So now, considering all these factors into account, if we take the aggregation here, you can see that how the different controller and different aggregator, they may get integrated with each other through the fast charging station. And then there may be some different levels also. So for example, we may have EV charging station level, and on top of that, we may have charging station aggregation level, and on top of that, we may have the power system operation level. So of course, pricing is going to be a very important factor also, and dynamics of the pricing also. And of course, we have to consider here the resources and expected charging demand also. So every unit or every fast charging may have their own controller also, and then aggregation. If suppose some of them have been owned by one company, then they may do the aggregation at the upper level also. So depending on how many competitors are there, and of course, like every aggregators, right? So they have to consider the grid constraints within the distributed network, and of course the market pricing also. So here you can see that how complicated it is going to be there for doing the charging management and optimum scheduling also. So maybe now we have to move forward because the time is running also. So we all these things what I have explained you, that is a priority based coordinated electric vehicle charging system for heterogeneous user. So that paper, I think I missed to include the DOI there, is already published. You can refer that. So then in another paper, we have reported all mathematical modeling with all probabilities and with all approaches of expected arrival of electric vehicles and how we have to do the resource allocation, right? That queue-based dynamic charging resource allocation and coordination of heterogeneous tropics in electric vehicle charging station is provided in paper B. Like, so if you are interested, you can refer them. And most of these articles, right, they are open essays. So feel free to download and read them, utilize the learning from these papers for your research work, for your teaching, or maybe giving the lectures to the industry on electric vehicles also. Then another one which is very interesting, that how we have to optimize the charging resources at the fast charging station with opportunistic electric vehicle users, because we know that there may be a lot of opportunistic electric vehicles compared to primary users. So then how we have to optimize the available resources for fulfilling the requirement of the opportunistic electric vehicle users by using adaptive charging that have been very systematically presented in this article. If you are interested, please download that article and read it. Then another very interesting thing, which is very important, because when we are talking about the fast charging station, we are talking about the coordination, right? And we are responsible for that one considering the local condition. So of course, there may be some equipment failures and repairs also for regular operation and maintenance also. So how those are going to impact the reliability of the fast charging station, that is also very important. And that work have been reported in paper D, and that is also again the open access article. So I request you to understand all these things. Please download that one and read it carefully. Then overall conclusion is that we need to have fast charging station, and this fast charging station, of course, we need to use some international standards for those charging pools. But locally, how we have to manage those charging pool, considering the available resources and the expected demand, we may need to develop appropriate architecture for that fast charging station. Okay, so with reference to that, if you are interested to develop the DC microgrid architecture, considering the voltage sustainability and providing the dispatchable power from a dispatchable source as per the requirement, then you can do the Google search, and you can, or maybe Google Scholar, maybe I should say. So within that Google Scholar, you find some of my articles. They are open essays also. But when we are moving towards the fast charging station, the important thing is that to find the optimal location, and then of course the sizing also, right? And then before deploying such a fast charging station at an optimum location, we have to do some performance assessment also under different conditions, considering the profit and other performance parameters. For example, resource utilization, blockage, service interruptions, charging completion, waiting time in the system, etc. Then there are a lot of scope for doing further research work, which is going to be very useful for upcoming demand of the electric vehicles, right? And we can work on that not only on designing and developing fast charging station, but of course doing some charging coordination, but taking into account uncertainties which we discussed earlier. And all these topics still we need to work hard in making the users more attractive towards the electric vehicles, because if the users are satisfied, more electric vehicles will come into the market. Of course, government need to develop some more policies for increasing the electric vehicles. You may be aware that in Norway, last 2 years, maybe I can say, 99% new vehicles which have been sold into the market, they have been pure electric vehicles. On the road, if we see out of 10, maybe 7, I can say, 7 vehicles, they are pure electric, including the electric buses and heavy duty trucks also. One of my students, she is working on electric vehicle bus charging management, okay, taking into account the rural distribution network. And she has started the PhD few months before. So still we have not received any results from her work. But earlier, one of my students, she did wonderful work in which she developed some methodology for doing the en route charging of the electric buses to extend the range. Okay, that work have been recognized as the best thesis also, and I believe that some of the outcome from that work have been incorporated by Siemens also, algorithms basically for doing the en route charging. So that work is also really interesting, and that is also available open access. If you are interested, you can refer that one. Some of these are the references which you can refer for this work. Then another very interesting thing, we have to consider utilization of local energy resources. So I will not go in much detail, but this work also we did, in which we used AC microgrid architecture, and within that AC microgrid architecture, we integrated group functionality with energy storage for fulfilling these expected dynamic demand of the electric vehicles. So that is also very important, and if you are interested, you can refer that one. So here's some of the architecture which I have given here, but much more detail about this, they are available in some of my publications also. Okay, so here you can see that with reference to the converters, especially for the dispatchable source, how the group functionality have been incorporated in these power conditioning devices, that work have been really interesting. And then making the photovoltaic based active generator, or maybe in a simple way operating as a virtual synchronous generator. So to make it that more interesting, we put two type of electrochemical energy storage depending on their discharge characteristics, and accordingly the different group functionality have been introduced in this DC-DC converters, especially for the energy storage, for dispatching the power, right? Here the load means electric vehicle charging station using hierarchical control. And the details are available in some of our publications also. I will not go in much more detail, because otherwise I'm also getting bored and you will also get bored in that one. Okay. So this is a very interesting work also, if you are interested understanding the AC microgrid architecture for operating local distributed energy sources. So here you can refer some of these articles, right, which are available, and most of them, they are the open access. Okay, so we have to see that how we are going to develop the microgrid architecture, how we have to select the distributed energy resources, how we have to do the coordination among them, and which type of AC or DC microgrid architecture which we can utilize, and accordingly we can go. So I will not. Then another one, if you are interested, you can refer one of my book which has been published by Elsevier, and this book, it was in cooperation with in Napier Edinburgh University and myself, and in which we tried to analyze how the government policies are going to impact the penetration of electric vehicles. It has been published long back, so the data may be now old. And in that book, there is a one chapter for the India also. Okay, and some of the results what we discussed with reference to today's lecture, they are available in this PhD thesis of my candidate, and that thesis is available open access from my university website. So if you are interested, you can download that one. Then another very interesting thing that I did one work in cooperation with Napier Edinburgh University, in which we try to integrate solar photovoltaic panel on the vehicles, and then how these vehicles can operate under the varying condition when we have the solar photovoltaic panels, right? And how that can help us for extending the range, or maybe in a simple way doing the ventilation system, or with much more focus on heating, ventilation, air conditioning system. And here you can see this is a very interesting car. So with reference to that, so some of the publications are there. If you are interested, you can refer that. Now coming back to this point, this is my car. Okay, so this is my car which I am using now. Here you can see that it has a two photovoltaic panels of 180 watt. Its energy conversion efficiency is 22.5, and this is also plug-in hybrid electric vehicles. So with one full charge, it can go up to 50 to 55 kilometer. And these panels, they are providing the electricity for the heating ventilation purpose also. And also, of course, it operates under the hybrid mode also. And under the hybrid mode, it gives the average of around 3.5 liter of fuel consumption for 100 kilometers. It is a quite fuel efficient car. So being an engineer, we need to work on hybrid technology. That's why I'm using this car, in which, right, we have photovoltaic panel, renewable energy, plug-in electric vehicle also, and hybrid also, in which internal combustion engine there. And you can see that I did this work long back, right, in 2019. Okay, and some of the outcome from this work, right, because it was more like a research based within the university, that work have been used by some of the leading car manufacturers, for example, Toyota and others also. Okay, so by saying this one, I'm concluding my today's lecture here. Okay, so now if you have any questions or would like to give any feedback, please feel free.
Thank you very much, sir. Any questions from any of the participants, please, for this, sir?
Hi, sir. I'm audible.
Yes, you are.
Sir, first of all, thanks for sharing that wonderful research work. And I'm also working in that particular areas. But main problem we are facing that we are not able to get the charging discharging data. That is the biggest problem we are facing.
So what do you mean by charging, discharging data for electric vehicles, you mean, right?
Yes, sir.
So that charging and discharging data, in a very simple manner, is going to depend on the driving patterns or driving cycles. Which type of driving cycles we are considering? You can utilize some North American or European Union driving patterns, which have been widely used for such type of work. But those driving patterns of the driving cycles, let's say, may not be useful considering the Indian scenarios. In Indian scenario, the vehicles, they have a very different type of driving patterns due to the traffic congestions in the urban area, right? Maybe in the suburban areas, it may be different. In the rural areas, it may be different. So these driving cycles are going to impact your discharging patterns of your electric vehicles. That patterns you have to integrate as a load on your electric vehicle performance for getting the requirements of charge.
Okay, thank you, sir. One more question. Sir, you have shared that the negative impact of the fast charging on the grid. Is there have any negative impact of fast charging on the battery of the electrical vehicle?
No, because most of the car manufacturer, they are manufacturing the car of let's say around 100 kilowatt hour capacity, and they want to get it charged from 20% to 80% state of charge within the 15 minutes. And considering those factors, those international standards have been developed. So there is not going to be having any impact on the life of the battery between 20% to 80%. But the inbuilt battery charging management unit of the electric vehicles, they may operate when battery is charged up to 80%. To make from 80 to 90%, then it may take more time also, because then they don't want to damage the battery cells. And then for that, then it needs more time, right? So then that timing factors and pricing also is integrated in this charging pricing, which have been implemented or on the user by the fast charging station operator.
Thank you, sir. One more last question. You have shown one navigation platform uh,
Mhm.
for your work, FCS charging. Where we install that navigation platform? It is installed inside the electrical vehicle.
Yes, of course, because if you take, for example, if I take a Tesla Model Y, so it has a all inbuilt navigation platform, and it identifies. I'm talking about the now from the Norwegian perspective point of view, or Norwegian context point of view. So that navigation platform, it shows that which nearest electric vehicle charging station is available, and it doesn't give that much information, but it gives that how many charging ports are available there, and with capacity available.
How they are sharing the data? I think navigation is feasible. How they are sharing the data? That how many
So
charges?
they are sharing the data using this ICT infrastructure. Okay, so for that, I mean, basically we have to utilize this mobile operators, right? So they are using this mobile operator, and then this mobile operator, they may have given some dedicated bandwidth also there, or that basically.
Thank you, sir.
So it is not just only the electrical engineering solution, but we need to integrate different disciplines, industry players also.
Sir, I have one question, sir.
Yes, please.
Sir, how motor act as a generator during regenerative braking, sir? During regenerative braking.
Yes, of course.
Because we are applying brake, the motor will start rotate, it will speed will
Yeah.
reduce, right? Then how
Yeah.
it will generate?
Basically, it's very simple, because I have this vehicle that is a plug-in hybrid electric vehicles with solar. So automatically, whenever I'm reducing or braking, or when we have the slope also, so automatically it becomes regenerative and motor brings some generator, and that generated energy has been stored into the battery bank, and it is very dynamic. A fraction of seconds it changes in milliseconds of time. Very dynamic. And again, it depends, like, then basically it is not, we cannot control that one, but then that is from the manufacturer point of view, which type of drive system they are using, right? And how that drives, right, is operating under the motor mode and the generator mode, and how fast, right, that control system is going to work. So that is again very interesting point here. But our research work is more focused on charging management, because we thought this charging resources management for every location is going to be very different, and there is a lot of scope for doing further research and useful for the planning and the developing policies also. Any further question?
Okay, sir. Thank you, sir. Thank you.
Thank you very much, sir. So one question is
no.
there in the chat window. How the battery size and its capacity is decided, and what would be the parameters under consideration for that?
Please repeat again.
It's the how battery size and its capacity is decided, and what would be the parameters under consideration?
So, are you meaning the battery within the electric vehicles or at the fast charging station?
So this would be, I think, for the electric vehicles only.
Within the electric vehicles, of course, everyone want to have the higher capacity, then we get more autonomy range. So make it more simple. Around 100 kilowatt hour battery, right, is required for around, let's say, 400 to 450 kilometer range. And everyone want to have higher autonomy range. Okay, nobody want to have their car just for 100 kilometers, right? So that is the factor there.
Right, so this was the question from Dr. Ujjwala. So I think that addressed his query, sir. Any other query from the participants, or we would be continue? Okay.
So I have a query, sir. Good evening.
Yes, please.
So is it DC microgrid is safe and prominent for fast charging than AC, sir? Since we are facing a lot of power quality issues when we are connecting multiple charging stations.
Yeah. Personally, what I feel that DC microgrid may be a better option for the decentralized approaches like a fast charging station, right? And then, of course, the power quality issues can be solved easily. But with the DC microgrid, the main technical challenge may be if we want to integrate conventional synchronous generator based dispatchable source, then we may have some control and operational issues also. We have to work on that one. And if we want to understand that control challenges, you can refer some of my work which was in cooperation with VNIT Nagpur. Okay, you can do the search in Google Scholar and you will find. And most of the publications, they are open access related to your question.
Thank you so much, sir.
Very good. Any other person want to ask?
Thank you very
any
much, sir.
question?
I think
Yeah.
with this, we would be yes. Any other one participants, or we should continue with the formal closing of the session? I think there is no query now, sir. All the participants very actively participated and asked the queries from you, sir, and you addressed it very well. So
Thank you.
I am
Yeah.
very much thankful you have accepted our invitation and be part of this FTP, and all the participants gain the benefit from your expertise in this particular domain area. And
Thank
the way that you have described everything from a simpler way, that is very commendable, sir. We are very, very thankful to you, sir. And I would request all the participants to please switch on your webcam so that we can have a group photograph.
Thank you, Preeti.
Thank you very much, sir.
Today it was a really hectic day for me. In the morning, I have 2 hours lecture on the wind
Oh,
analytical
okay.
version also. But then I promise
Your
this. So again,
your
this
expertise
lecture.
is always required, sir. We are that's why you're always engaged, sir.
Initially, I was thinking maybe to request you to postpone my lecture on Saturday. Then I thought, okay,
Oh,
that you might have all other commitments, but I will manage it. But
right.
we managed well. Thank you.
Thank you very much, sir. Thank you very much, sir. So, Rahulji, I would request to please take the screenshots of the photograph.
Yes, ma'am, done.
Okay, thank you very much. Thank you very much, sir.
Thank you. Eh?
Thank you. Thank you very much, sir.
Bye bye.
Thank you. All the participants, please be connected, and our next expert will be joining soon on this link. And he has already joined. Good evening, Rahul, sir. Am I audible to you?
Yes, ma'am. Good evening. Good evening to everyone.
Good evening, sir. So, with your due permission, can we start the session, sir?
Sure, ma'am. We can.
Sure. Thank you very much, sir.
So, shall I directly
Sir,
share my
just
screen?
before starting, yes, sir, you may share the screen. Rahulji, please make the sir the co-host. And before starting the session formally, I would like to introduce.
Done, ma'am.
Ma'am, I guess I cannot hear anyone, or I cannot hear you, ma'am. Am I audible?
Yes, sir, you're audible, sir. Am I audible to you, sir?
Yes, ma'am. Now I can hear you. Yes.
Okay.
Good evening, everyone. We are now proceeding with the next session for today. And Rahul, sir, it's my pleasure to introduce you, who is the today's speaker. He is a visionary in India's electric mobility revolution, and he is the Chief Technological Officer and co-founder of EVI Technologies Private Limited and Director at Himachal EV Infra Network Private Limited. With more than 8 years of groundbreaking work in EV charging infrastructure, smart grids, renewable energy integration, and end-to-end product design, Rouser has been at the forefront of India's most significant EV milestone, from winning the first ever EESL EV charging station tender in 2017 to installing the Delhi Metro's first on-premise EV chargers and deploying the thousands of chargers nationwide for IOCL, BPCL, and HPCL. Beyond hardware, Raul sir has led cutting-edge software development, creating charge point management systems and mobile applications for DRIIV, an initiative of the PSA to the Government of India and IIT Delhi that has enabled the smarter and more connected charging networks. Sir has designed everything from advanced AC and DC chargers to battery swapping stations with Japanese tech leader Murata and high-end DC charger controllers for BHEL. He had pursued Masters in Electronics from Department of Electronic Sciences, Delhi University, and also contributed to research and training with IIT Delhi, TERAI, and Mercedes-Benz R&D India. Passionate about turning ideas into fully functional products, he has shared today to share his insights on electric mobility and the vast opportunities in its offers. So we heartily welcome you, sir, on this third day of FDP, and the session is over to you now, sir. Screen is visible, sir.
All right, so I hope my screen is completely visible and it is in
Yes, sir,
the
it's visible.
presentation mode.
Right, sir.
Okay, so first of all, thank you, Preeti ma'am, for inviting me in this wonderful session and making me a part of it. So, good evening, everyone. I live nearby airport, so if by any chance, whenever there is a flight goes, so there may be some network break. So I really apologize for that. And if this happens, so I will, share the things which you might be missing. So today we will discuss about smart charging systems for e-mobility. And so for that, I will just go through in a very brief manner about EV charging. So as you can see on the left-hand side of this particular slide, the top image is mainly fueling an IC engine. And similarly, we fuel or we charge the electric vehicle also. So basically, what is charging of electric vehicles? The charging of electric vehicles is a process to refilling the energy of the battery from different sources. So that different source may be grid, solar, or battery bank. And this is mainly being done by connecting the EVSC socket or gun to the car. And this is a process flow, which is very important. So in this case, in case of EV charging, so we have a grid, solar, or battery bank. It connects with the charging station, and then it connects with the EVSE, which is electric vehicle supply equipment, and then to the electric vehicle. So the EVSEs are majorly categorized into two part. One is AC charging and second is DC charging. So I believe you all must be aware of this. So I just wanted to tell you the major difference. In case of AC charging, there is an onboard charger present in the EV. Here we can see two cars, one with AC charging and another with DC charging. So in this case of AC charging, it gets AC current from grid and supplies AC to the vehicle. Then the onboard charger converts that AC into DC to supply the power or the energy to the battery. In case of DC, it bypasses the onboard charger and it directly charges the battery. AC chargers are mainly slow, DC chargers are mainly fast. AC chargers are mainly having low level of communication like PWM communication, and DC chargers are having digital type of communication in which they exchanges the messages. So why I was telling you about AC charging and DC charging in smart EV charging. So in case of smart charging, this charger or EVS, electric vehicle supply equipment, is the most important component of the whole ecosystem. So now, as I have told you about the EV and EV charging, so this is you know the reason of this EV boom also, like we are having this session. So it is growing very rapidly. The EV adoption is having more than 29,277 EV chargers, and we have a target of 30% of whole electric vehicle by 2030. And you can see from one of the report that in Jan 25, more than only in 1 month, more than 59,000 three-wheelers were sold. And you can see this about through this map, like how the EV chargers, like public charging stations, are being distributed across the India. But with rapid increase in EVs and rapid increase in the chargers, so this is going to be maybe a threat or a constraint to the grid, because more so we have just studied that EV requires power from the grid, right? And it comes through the charger or EVSE. So ultimately we have the grid constraint, which means we have to do something to either to the grid or to the charger to manage this unmanaged challenges, which means we have, like as you can see from the grid, we have generation, transmission, distribution substation, feeders, service transformer, and service cables. So generation is done in another city, transmission again throughout the city, and then we have a distribution substation, and then we have feeders. So you can see from the grid point of view, this service cable and the service transformer are going to face the major challenges because of the EV or upcoming EV requirement from India. And along with that, there is a technical term, or there is a phrase called as 6 p.m. spike. So that is a peak load hours, which means when you can see the electricity use throughout the day. So it is under, certain range. But suddenly when everybody like reaches home around 6 p.m., they plug in their vehicle to the charger. So there is a sudden spike. So this spike can lead to voltage fluctuations, transformer failures, and blackouts. So maybe 5-10 years before, or maybe 3-4 years before, all of you might have experienced in your region where you belong from, that there are there were cases of transformer failure, due to which we had to suffer from electricity failure as well. So that is because when the summer comes, so there is a huge every home has multiple ACs. So when at the evening, when everybody switch on the AC, then the transformer failure occurs, and due to that we have faced the blackout. So similar kind of uh, thing are going to happen for EVs as well, because EV is again everybody reaches home around 7 p.m., 6 p.m., and they want to plug the vehicle for the charging. That is why during the peak hours, there will be a high tariff. Like if normally if we talk about, then the tariff may be 6 rupees, then during the peak hours the tariff would be 8 rupees or 10 rupees. So this is the very big problem. One is the surges, second is the blackouts or damages in the transformer and the grid, third is the tariffs. So we will see how all these challenges are being taken care by the smart charging in EV mobility. So let us understand what is a smart charging. So smart charging is the intelligent management and control of an EVSE, which means EV charging session. So as we have seen, there is a tariff problem, then there is a power delivery or power requirement problem, and then there is a time problem also, because everybody wants to charge their vehicle at a faster rate. Nobody wants to wait, right? So we can see from this diagram, it is very much clear that it is like a flow diagram or block diagram of smart EV charging, in which the most or the important part is the grid connection, as you can see from the bottom left. So the other energy request, it can come from solar, wind, or grid. So it goes to the EVSE, which is a smart charging station, and there is the communication. So green part is the communication. So communication happens through Wi-Fi, Bluetooth, or GSM. So this is a communication network. So in which the user on the right top, the user tells the demand and connects the EV to the EVSE, and then the EVSE delivers the power or the available power from the grid to the EV. And through all this management, user is able to do the cost saving and is able to save the power also and save the load also. So we will understand step by step in detail how all this happens. We will go through some technical data also. Just a minute. Yeah. So as we can see, there are three dimensions of energy flow in case of smart charging. One is time. So you can control when to start the charging and when to stop it or pause it. And then you can control the power or rate of charging, how much current you want to deliver or how much kilowatt you want to deliver to the battery or the EV. Then you can also control the direction, which means you can take power from the grid also, from the EV also, whenever it is required. So that is the most important aspect of any smart charging, that your EV can be worked as a battery bank or battery module and can supply power or energy to the grid, which can stabilize the peak hours, or which can stabilize the charging or the grid curve. So in case of unidirectional charging, the power flow is from grid energy, then to house, or then AC charger, and then to electric car. And in bidirectional, which we usually refers as V2G or V2H, is from both direction, maybe like from grid to car and from car to grid as well. So we on the right hand side we can see that we can see the difference between smart charging for EV and electric vehicle and fast charging. So there are two type of charging. One is the traditional, or we call it as dumb charging, and the smart charging. So in case of dumb charging, the charging flexibility cannot be adjusted as per the grid power. So but in case of smart charging, the charging flexibility is there, which means you can actually schedule your charging maybe from 8 p.m. or maybe from 2 a.m. or maybe from 4 a.m. whenever the load is at a lower utilization, or the peak hour are not there, or the off peak hours are there. And you can control or optimize the charging speed also, which it was not the case earlier. Why? Because you have to supply the constant current or constant power throughout the charging session. But in case of smart charging, you can vary the charging speed also. You can like, let's suppose you have a battery of 30 kilowatt hour, and you want to, if you simply charge it with a 7 kilowatt charger, you can charge it at a constant rate of around 6 to 7 hours. But suppose you have some load utilization at your house or at somewhere else, then you can reduce the power of the charger, and you can increase the charging time or charging, or decrease the charging speed. Then cost efficiency is also there in case of smart charging, because you can integrate your smart charger with the smart grid concept, where when the when the tariff is low, then you start your charging. And then the battery life is also increased in the case of EV. How? Because when you avoid overcharging, or when you control the charging, then the battery draws less power and it balances the cells at the extreme or at the end of the charging. And again, the environmental impact will also be there, because you can charge your vehicle from solar or wind or some renewable energy present at any place whenever you go for charging. And earlier the renewable energy was not into very much of picture, so we were dependent on the fossil fuels. So this is basically the EV charging ecosystem. So I will take some time and describe everything which you are seeing on the screen. So we have a power grid, we have EV charging software companies, we have CPOs, we have EMSP, we have home chargers, drivers, charging station manufacturers, EV manufacturers, and power sources. So as you can say, we should start from the power sources. So from the power sources, there are sources like hydropower, fossil fuels, and then wind energy, solar energy, and XYZ. So it generates the power and battery bank also. Then it gives power to the power grid, and power grid do the distribution of the energy. And then after that, it connects to the EV. This is not in the sequential manner, and then it connects to the EV charging stations, right? So it is mainly for the company perspective. So in case of EV, the role of the EV charging software company is, so they develop the software for end user. They develop the software for the charge point operator who to manage the chargers and to maintain a communication between the grid and the chargers for the load demand management. And then the CPO is charge point operator, which the role of the CPO is they have to operate the charging stations. EMSP is electric mobility service provider. These are mainly like the mobile application provider where you visit and navigate the charging station, do your payment and charge your vehicle from, and you can remotely start and stop charging. Home chargers are the provider which provides the charger for your home purposes and which you install at your home. And EV drivers, like as the user of the EV or the charging station will be considered as EV drivers. And charging station manufacturers are who are developing those EV charging stations, like completely who are making those charging stations, and EV manufacturers are who are making those EV. So all of this going to impact because of the charging and EV charging. So that is why they all are part of the EV charging ecosystem. So here I have taken few important part from the grid point of view for the EV charging ecosystem. So as you can see, there is an EV driver, and then there is a MSP. MSP is called as mobility service provider. So EV driver with its car, they take a subscription from e-mobility service provider, and then e-mobility service provider has to have the communication with the charge point operator. So charge point operator is actually having the physical charging station, or you can call it as they are the actual charging station owner, where we have the chargers installed and where the EV will go and start charging. Then they both, CPO and EMSP, both communicates with each other through hub. So that is called as roaming platform. Roaming platform means one MSP or one EMSP can communicate with other CPOs also. And this charging station is connected with the electricity supply. So there are majorly 4 layers for this system of smart charging. So one is the vehicle side. So if you do not have the smart BMS in the battery, then you cannot control the power to be delivered to the battery cells through that BMS. So we need to have the vehicle side also. Then we need to have the charger layer, which means the control unit, which has the AC, DC, and smart AC, smart DC chargers. Then the cloud layer, which we call as brain also, where we have the central management system, and then we have a grid layer, which means the supply or the utility part. So these are the hardware requirements for the smart control system. So you can see from the below block diagram, or system diagram. So there is an AC input, and then we have AC input protections. Then we have energy meter direct supply, and then relay, and then AC power output. And along with that, we have controller units where we have external communication with the communication interface. Through this communication only, the device communicates with the backend or the CMS, where the message exchange happens for the smart charging. So currently I'm telling the product about the product from overall perspective. Then we will go towards into detail of the smart charging. First of all, we have to understand about the product itself, and then there is a vehicle communication side also, because it is a smart charger or smart component control system, so it has to communicate with the vehicle, and this is a type 2 AC charging controller or the charging gun. So that the standard for that is IS 17017. So along from this, what we have understood is we have a relay which controls the power on or power off to the EV. We have a communication interface which communicates to the from with the backend to receive the messages from the grid or from the central management system. As you can see from here, the CPU is directly connected with the grid, and grid gives the so it gives the commands to the charger. So grid directly does not give the command to the charger, but it gives through the CPU. And why we like by saying CPU, which we means the software platform. And after that, so this is the basic block diagram of our smart EV charger, which is a very important part of the EV charging ecosystem for smart charging. And after that, we have to understand the protocols. Protocols, which means communication protocols. There are majorly, we will talk about three communication protocol. One is this vehicle to charge with charger, which means like communication between the EV and the EVSE, which is basically as per the standard, which is IEC 61851 or IS 17017. IS means Indian standard, this is international standard. So through this communication, car can tell the charger that this is the maximum capacity, or charger can tell the car this is the maximum, power available. Similarly, the charger communicates with the cloud or the remote management, and what is the importance of this communication is it tells the charger to set the current. Like it can tell that set the current to 16 ampere, or it can tell the charger to set the current at 20 ampere, like that. And then between server to server, which means one, we have EV, I think, yeah, it is there. So we have EV, then we have charger, then we have cloud CMS, and then we have roaming integration, which means other platforms can communicate with each other. So I will tell you all what we have read from here is I will tell you in this diagram. So this diagram may seems a little bit complicated or complex, so I will try to explain it in a simpler form. Just follow my directions. We will see from the very left hand side. So you can see it is written as EV OEM, which means we have EV OEM, which means like EV manufacturers. So they have a non-standard communication protocol for EV. So the important is EV here. So you can see EV is communicating with EVSE from first point, vehicle to charger, which means EV, electric vehicle, to electric charger and charging. So charging station can have more than one EVSE, and then all EVSE can charge one EVSE can charge one EV at a time. So you can see, and this is a standardized protocol, which here we have a DC protocol written here, ISO 15118. Here I was mentioning about AC charging protocol, which is IEC 61851. And this EV charging station communicates with the central charging station management system, which was the second point, charger to cloud. So this communicates over a standardized protocol, which is called as OCPP, which means Open Charge Point Protocol. We will just see about this. And then there may be multiple CMSs also. Like I'm sitting in Delhi, anyone might be sitting in some other region, maybe Uttar Pradesh or Mumbai or Karnataka. So every state can have their own charging station, physical stations, and all those different charging stations may be operated by different charge point operators, and all different charge point operators may have their own charging station management system. But suppose if I am traveling from Delhi to Mumbai or to UP, then I have to again download or register to another that regional CMS. But so to avoid all of that, we have a EMSP role, which is called as Electric Mobility Service Provider. So it is his role, not the EV user role. It is his role to communicate between different CMSs and have all the data with them. It is as similar as we have Make My Trip, we have Paytm. So you can book the same flight, same seat from Make My Trip app also, and you can book from the flight aggregator also, like Air India or Air Asia, or like Indigo, or you can similarly book the same flight from Paytm also. So Paytm and Make My Trip, they are like EMSP, like electric. So they are the service provider, and CMS is like Air Asia or Indigo. So those are having real asset, like, or real flights, or in this case real charging stations. But you can have cross-platform integration, through which one platform can be used to book different charging sessions, or in the case of flight, to book different flights, correct? And there are two approaches in that case. Suppose we have a government intervention also. So in case of government intervention, this concept called as hub or roaming platform. So this is called as hub. So what is a hub is all the EMSPs or all the CMSs, they send their data to this particular hub. So there were two methods. One method was to peer-to-peer communication, like one EMSP will talk to this CMS, and this EMSP will talk to another CMS. So this is having communication with different CMSs. There is no centralized data or communication is happening. But in case of hub, all the CMS will send the data to the hub, and all the EMSPs, service provider, will fetch the data or take the data from this hub. And you can see there are two different protocol happening. One is OICP and another is OCPI. So OCPI is Open Charge Point Interface, where the communication happens between EMSP and CMS, like one-to-one communication. And Open Interchange Protocol, which means OICP, is between the CMS and the hub, EMSP and the hub. I hope we can understand from this diagram. So I can move next to the next. So when I have mentioned, the EV and the EVSE communication. So you can see the roles, because in case of any type of communication, there are roles between one entity and the other entity. So in case of EVSE, which stands for Electric Vehicle Supply Equipment, it delivers power to the EV with all safety considerations, right? And in case of EV, it consumes the power or sink from the grid through EVSE with all the safety. So safety is there with both the entities. And then to tell EV about the power, so it tells EVSE tells the power availability, like this much of power I have, and EV adjusts the load. Like EV adjusts the load so that it can take the power from the charger, so it does not overload. It triggers the overload condition, correct? So it will tell the PWM current availability through the PWM signal. This is the communication part. So there is a PWM, pulse width modulation signal happens. So it tells through the duty cycle. So this much of duty cycle is there. It means this much of power or the current can be drawn or can be is available, right? And it tells about the state of the EV charging through voltage change. So this is basically the communication, very basic communication between an EVSE and EV, and it is we are following an AC communication. This is for the AC type 2 communication, right? It generates 1 kilohertz PWM cycle, and the duty cycle goes from 7% to 90%. So as I have mentioned about the OCPP, so we have it is the most important protocol in EV charging ecosystem, because every EVSE or every charger communicates over OCPP, and the smart charging, which is the most credible or most important topic, it functions through this protocol, which means the OCPP has the provision to implement smart charging. So you can see it is a communication between charge point or central system, and flexibility is it can operate multiple hardwares and multiple softwares also from vendor A to vendor B, which means suppose the charger is from Tata Power and the software is from GOBP. So this protocol enables both the hardware which is a charger and the software which is a CMS to communicate with each other through a protocol, correct? And communication role is charge point is a client and it sends the updates like heartbeat, meter values, start transaction, and central system is the server, and it controls the charger through remote start transaction and change configuration and set charging profile. And it enables the smart charging over complex timing and power based commands. So what smart charging really enables? So smart charging equals controlled and internal power delivery. So the most important part is, first of all, is the controlled, second is the intelligent power delivery, because if the power delivery is not controlled, then you may face a outrage, as I have mentioned in the earlier slides. So how that happens, that we will understand through this particular slide and onwards. So the central system, where I have mentioned in the previous slide, so this is the central system, which is a software. So that software has that algorithm how to distribute the current or the power across all the EV chargers or across all the regions or across all the EV charging stations. So you can see from here, gains the ability to influence the charging current or power of a specific EV or the entire group of chargers. So it has the capability, like it is being controlled, because as we know that all the chargers has to be an IoT device. It has to communicate with some central system, and through that central system, all the commands are being transferred or message being sent to control all this charging current and power. And what are the decisions constraint? Like it is based on the grid constraint, energy availability, building wiring limits, and user priorities. So these are the main key factor in case of smart charging. Like these are the uh, drivers of the decision made by the central management system. So one is the grid constraint, which means how much grid availability is there, or how much like peak, if there is a peak hour or not, and the energy availability, which means like if it is a solar based energy which is available in the daytime, or if we have a battery backup for that, we have a backup capacity over there or not. And then building wiring, suppose we have a low capacity wiring installed, we just putting, you know, the capacity, we have a 16 ampere plug only in the house, so we have to change the power delivery of the charger through the CMS. And the user priorities. For example, if I'm reaching to a hotel or maybe some parking in the public, and I have to, you know, go in 1 hour. Like I'm going to consume it for 1 hour only, and I want 30% of SOC, or I want a higher, battery charging. So I will definitely require a fast charging for my car. And suppose if I'm going to watch a movie in which I am going to stay in that particular mall or theater for at least 3 to 4 hours. So in that case, I have a 4 hours of time. Then I can have a, or I can ask for a a smaller or a slower rate of charging, in which the cost will be at a lower than the faster charging. And then all the adjustments are being applied through the charging profiles. Charging profiles means the structured rules defining how much energy or power can be delivered at a specific time. So in this diagram, you can simply see then the total flow limit set on the back end is 90 ampere. So, but there are 4 chargers, right? So in 4 chargers, all of those chargers can charge at a maximum capacity of 30 ampere. So in this case, all the limits are being provided by the CMS through the software and the communication protocol, and these are the real time. Let us suppose uh, for example, if it is 90 ampere, or let us suppose 100 ampere. So every charger will get 25 ampere of capacity. It's basic maths, like 100 divided by 4. And but if this charger is having a priority car, so it will give maximum like 30 ampere to this charger and will reduce the power of other chargers. So that is the capability of a smart charging. Correct. And now suppose if this is not, happening, there is nothing connected on the 4th or the 2nd of the charger, but so that is why the current is 0. Now, if 4th vehicle comes in this particular case, so if 4th vehicle comes and he wants to have the maximum power, so it will give 30 here, and it should reduce 10 10 10 from all of the 3. So all this mathematics or all this process comes under the smart charging. So this is all enabled by the smart charging concept. So let us understand about the charging profiles. So charging profiles are also known as the blueprint for the power control, because through these profiles only we control everything in the charging sessions. So in this case, what we define is we define the limits on the charging power or current at different moments. So suppose like in case of 24 hours, the charging power or like I have a 7 kilowatt charger. So in case of low peak hours, I can have the maximum capacity out from the charger, which is 7 kilowatt. And in case of peak hours, so I can reduce the power to 1 kilowatt or 2 kilowatt, so that other appliances can be utilized properly. Let us suppose I have a load availability of 10 kilowatt for my house or for my office, like that. And when it is like 8 a.m. in the morning, and in case of winter, we all uses like geysers and all that. So in that case, the power goes 2 kilowatt power goes to the geyser and some other appliances like washing machine and all that. So let us suppose 3 to 4 kilowatt is being utilized by the house only, and then rest of the power goes to the charger. Similarly, during the daytime when nobody is at home, and let us suppose if it is Sunday or something, but we are not using the geyser or not washing the clothes. So in that case, the power is very less, because maybe lights are also not being utilized properly, or if it is like winter, so AC is also not there. So during that time, the peak hour is not there. So you can charge your car at a faster rate. So this kind of management or this kind of changing in the rate of the charging comes under the smart charging. So there are different type of charging profiles here. You can see it is charging limit profile, which means you are limiting the maximum current or power in a particular time window. Then second is scheduled based profile. Profile means like you are defining some set of rules for a particular charging session. It is a time of day limit. Time of day meaning you are charging your vehicle at midnight or at 2 a.m., but you are not physically going there at that time and starting your charging. You are just scheduling it. Like you have plugged your EVSE to the EV at 7 p.m. suppose, but you don't want to start your charging at 7 p.m. or at even 10 p.m. So through this smart charging, it will automatically be started at around maybe 2 a.m. or 3 a.m. whenever the load availability is there, or the um, costing or the tariff is very low. Then user centric profile is also there. Like suppose, as I have mentioned, I need in 1 hour I need maximum SOC. So I will need a faster, like my vehicle is 20% charge and I have to go to maybe 20-40 kilometers or maybe 80 kilometers. And I want my car to get charged at in 1 hour, I want it to get charged by 70%, like from 40% to 70% or 30% to 70%. Then it will set the power accordingly. Or suppose if I am there for a movie, then I need SOC from 40% to 70%, but in 4 hours, then it will give power according to that. Then site level is also there. So site level means like as I have mentioned, like if there is a campus, there are multiple cars are already there, right? So if multiple cars are being charged, so you can if more cars are coming, so you can redistribute the load availability or power availability amongst the charger based on the requirement. And then the dynamic profile, which means continuously varying. Like suppose your car is being charged for 8 hours, 7 hours. So you have just connected your EVSE with the EV, and based on the grid signals that this power is available, it may change in hours. Like maybe 2 hours later, the power availability is different, or maybe 4 hours later, the power availability is different. So this is all being done automatically in a very precise and controlled safety manner. So these are the practical use cases of charging profiles. So one is like peak load management, which is like a 6 p.m. Spike control. So as you can see from this picture, so the load maximum available for this particular house is 20 kilowatt, and the charge home power usage is available 12 kilowatt, and the charger is using 7 kilowatt. So if this 12 kilowatt changes, then you have to reduce the power of the charging output. Similarly, solar-based charging optimization. So it means like grid is also there, but solar integration you have done at your charging station or at your home. So during daytime when the peak hours are there, so you are feeding or you are utilizing the solar energy to reducing the dependency or burden on the grid. So that is also practical use of smart charging, because you don't know how much solar can be produced, at a particular instant, or how much load is available. Suppose the load availability from the grid during day, like at the maximum availability is 100 kilowatt, but during daytime, we can generate 40 kilowatt through this through the solar. So we will just take 60 kilowatt from the grid. So this kind of calculations and everything happens through the charging profiles only, right? And then load sharing across multiple chargers. So like as I have mentioned, like 100 ampere building feed 5 chargers dynamically shared, which means like the load is fixed and number of chargers are there, 5 chargers are there. So based on the availability, someone puts their charging at 7 p.m., someone puts 11 p.m., someone puts 3 p.m. So based on that, like if someone has done started the charging at 3 p.m., so he can have the maximum 100 ampere of the charging. But if it comes like at 7 p.m., someone else comes and start charging, so the charging current divided by 2, so 50 ampere to 150 ampere to second. And then other third person comes at 11 p.m. and I'm supposing like the charging cycle is first charging at 3 p.m. is already completed. So now again the load is distributed amongst the two new cars. So similarly, this dynamic changing of the power can happen through this charging profile. And then another is tariff based cost optimization, which is again at what particular time the tariff is there, you can change the rate of power to utilize the maximum cost availability of the from the grid. And then fleet charging control, where you have 100 of vehicles or maybe 50 of vehicles charging at the same location, and they are being charged overnight. So you can reduce the power and utilize the available load very strategically. So there are two type of charging. One is home charging, and second is public charging. So home charging, in case of home charging, the smart charging happens through the MDM input. So MDM is meter data management. So now you must be aware there is a concept or there is a product called as smart meter, which is connected or which is being installed throughout the India in every house. So in through that smart meter, they can sense the real-time load of the house or the building or the particular area, and can send the data to a HEMS or SEMS, Home Energy Smart Management, which is like a local brain of that particular house. So it takes the data from the smart meter, it takes the data from the charger, it takes the data from the AC and all the smart appliances. And so it is like a hardware to software integration, and this software to utility MDM, which means like meter data management, this is at the place of the DISCOM or the power distribution companies. So at their point of time or at their point, this MDM tells that particular house that this much of load is available, this much of load is being used at home, so this much of load is being you can use at smart chargers or charger point, right? And the smart control flow is, so the data comes from the charger or the smart meters, and then you can do a dynamic load balancing also, which means like if there is a peak hour. Again, I'm repeating this again, whenever there is a peak hour, so you are reducing the charging rate or charging power of the EV charger. And then again, the cost optimization is also there. So if multiple charging sessions are happening, so that can be done, a maximum like charging can be done at a lower cost, lowest cost or peak tariff window, which is again being provided by the MDM data only. So there are two type of load management. One is a static load management. Second is the dynamic load management. So in case of static data management, just a minute. So in case of static data management, so we fix a maximum power for a group of chargers. So the maximum charger like is the infrastructure capacity, which means like 10 cars plug in, each gets 10 kilowatt. Like if you have 100 kilowatt of limit, then you can have 10 cars charge for 10 kilowatt of charging at each point. And if you charge at two car are plugged in, so you just need like maximum of 10 kilowatt each, so 80 kilowatt is wasted. So this is like a static load management, in which you are actually like managing the load not on the basis of instant requirement, but giving up maximum availability to a particular like we have a home also, like at home also we get a sanction load of 1 kilowatt, 2 kilowatt, 3 kilowatt. So that is the maximum availability of the load, which is called a static load management. And if we want to increase the load, then we request to the utility, and then they again increase the load of 5 kilowatt or 6 kilowatt. But in case of dynamic load management, so real-time adjustment of charging power based on the instantaneous total power usage of the site. So in this case, so you don't need 100 kilowatt limit. So dynamically, whatever the requirement and the priority and the costing thing happens between the company and the user, so that can be utilized in a very efficient way. And then unutilized capacity can be allocated to another load, like in our case, charging. So if the charging is there and we have an excess load from that particular region, then the charging can happen at a faster rate. So the utility can get more gain, and this can be scheduled. So in this way only, the user gets to know that what is the off time period and how when they can start their charging. So it is like use case is mainly large offices, university campus, and apartments where site load fluctuates constantly. So second is so we have studied two type of load management. This is the third type of scheduled charging. So it is like a time of use. So when you are using the charging, and mainly everybody wants to use it at a lowest tariff, right? So basically we are doing it for the time. It is not mainly your accessibility, but mainly to do the cost optimization. So user inputs a required departure time, like for example 7 a.m. he has to leave or something, and the CMS calculates the minimum charging duration needed, and then the system schedules the charging to happen only during the off-peak tariff window, which means full battery is also charged and at a lower or lowest possible cost. So this kind of algorithm or this kind of intelligence is being implemented in the software or the charge point management system or the CMS. And the grid benefit is valley filling, which means shifting the load from the high demand to the low demand values. And you can see from this beautiful diagram also. So at around, like, you reach home at just right before 6 p.m., where the peak or the demand is very high, or we call it as peak period or peak time, right? So you have plugged in your vehicle, but you are not charging, or the charging is not happening here, right? And the time or the tariff at this time is $0.34, correct? Which is a peak time. But at a low peak or off time season, uh, during time of use, you can see that tariff is at 0.14 rupees, or sorry, dollar, and 0.11 dollar, which is a super off peak. So with the CMS, it calculates the requirement from the user, which is like a required departure time, and it calculates this type of graph is already just like 1 day before, or so 1 day before it is with the software. So it automatically detects, like at 12 midnight the charging will be started, and by 6 a.m. the charging will be completed. So you don't have to go, because in case of charging, as I have shown you in the first slide, so you have to really plug in a charging gun in the EV, right? As we do it in the petrol pump. But in case of petrol pump, or in case of IC engine, you cannot just plug in and remotely start or stop, right? Stop is automatically there. But in case of charging, you just need to plug in and go for anything else, like you can go at home, and then whenever the lowest, or as per the algorithm, it is there. So during this time, you can see the cost of charging is $7.14, and user saves around $388 per year. So that is how the smart charging helps user to save the cost. So it is again, money saved is money earned. So there are through the OCPP, there are different use cases of smart charging. One is, so I will I will show you some content, and then I will show you the image, and then I will explain. So first of all, the definition for this is like management of power distribution within single charging station that has multiple plugs or connectors. So it is like an internal charger management. Like you have a hub where you have maybe 20 chargers, 40 chargers, 50 chargers, where 50 vehicles are going to get charged. So in that case, this use case will be implemented, which is like a load balancing. And the goal is to ensure the total power drawn by the EV charging never exceeds its fixed electrical limit. So which means if the load sanction to that particular side is 100 kilowatt, and you have a 40 chargers of 10 kilowatt each, which means you have a requirement of 400 kilowatt. So your aim through this particular use case and using smart charging should be to ensure that the maximum utility or maximum utilization of that load should never exceed the fixed electrical limit, so that you don't get fine or you don't get any burn maybe in the cables, or you don't get any, extra charges. So the mechanism is the charge point is configured with a fixed maximum power limit. Charger's internal software continuously monitor the number of active EVs, and available power is dynamically redistributed among all the connected vehicles, which I have just given you an example of 4 EVs. So one EV at 3 p.m., maybe one EV at 7 p.m., then 11 p.m., and maybe in between also, maybe early morning somebody is coming 5 a.m. or something. So in that case, different because it is an EV hub, so maybe 1 a.m. also, 2 a.m. also, fleet operations happens 24 hours. So anytime they have to consider that the maximum load is not does not exceeds the fixed electrical limit. And strategies are equal sharing. So you can simply like if 100 kilowatt is available, you have 40 chargers, so you distribute equally, or prioritization can be done. So let us suppose 50 chargers are there and 100 kilowatt load is there, so you can equally divide 2 kilowatt to each. So that is one way of doing. Second way, all of those cars are plugged in, like 50 cars charging at the same time. So you are dividing each charger at a 2 kilowatt. Second strategy is like, suppose, as I have mentioned, you are there for 1 hour or half an hour. So you are dedicating 2 to 3 chargers or 4 chargers for their maximum power limit, like 10 kilowatt for 3 chargers, like 30 kilowatt you have allocated to just 3 chargers only, and rest of the chargers maybe equally or with respect to the priority you are allotting, right? So that way also you can have that. And so the application mainly is, so the application is parking garages, small office buildings, or any single site location with multiple charging outlets. So this is the diagram. So you can see the central system. It gets the grid connections, understand the load availability, then it communicates with different charge point, and you can see each charge point is having 2 connectors or 2 output. So this is like through OCPP charging profile. It sends the data to this, like and through control pilot signal, which I have just shown you in one of the slides. So I'll just go back to that slide here. So this is the communication between EVSE and EV. So this is mainly for the control pilot signal. So this is CP is control pilot only. So in this way, the charger or the EVSE or the connector tells the EV. This is a symbolical representation of an EV and the EV user together. So it sends the data or sends the power to the EV based on the data input from the central system. So here we have a single charging station and 2 charge point and 4 connectors with 2 EV plugged in. Second is central smart charging. Central smart charging means like in which you have a single central management system for a maybe particular state or nation or region, where you have a data not only for that particular location, but for many locations, like maybe 10. Here we have a data of one charging station where we have multiple charging points, right? But here we have a data of multiple charging stations. So there is a possibility, like in one region, like maybe Hodgepodge, there are 10 charging stations, and each charging station there is a different load requirement. So based on the requirement and the demand, requirement and the supply, they can redistribute the energy or the power. So here you can see those are not being integrated. So this is being integrated in a DSO, which means DISCOM. So here you can see the charge points are at a different locations, not connecting at a particular location. And here we can see all the charge points are being controlled by this central system, right? And it receives the capacity signal or price forecast from the utility, and then it calculates the new charging schedule for different like it has to predict how many charging sessions are going to happen in that particular day, and then it limits the power of the network at different locations. And again, the power and all that from EVSC to EV is being done through the charging protocol. And third is local smart charging. So in case of local, what happens is like charging limits are controlled by a dedicated local controller. So in this case, you don't have a central system. You have a local hardware on site so that there is a latency problem which happens through Wi-Fi communication or like that. So that is being reduced, right? And again, rest of the things are remaining the same, the dynamic load balancing and all that, but this is just a terminology difference. So here the central management system is sending one data to the local controller, and this local controller is redistributing the power or signals. Why? Because this central system earlier it was communicating with each charge point, or here you can see at each charge point, but here it is communicating with only one controller, which is a local controller, and it is sending data maybe through local communication, wired communication, or some Bluetooth or some Wi-Fi or some another network, mesh network. But here the load is reduced on the central system. As you can see, faster response time to sudden local load changes than a cloud-based central system. That is most important. So this is unidirectional smart charging, where we have a charging from one direction only, and it is being controlled through one point of node only. So like whatever we have discussed, technologies comes under V1G. V1G meaning we are only controlling the power or charging from the grid to the car. So it is the power flow into the car, but rate is controlled, right? We can control the rate. So second comes is V2G, which is vehicle to grid or bidirectional. V1G is unidirectional. This is bidirectional. In case of bidirectional, the energy flows from charger to car, or from car to charger, or car to grid. So both way it can communicate, right? So in this case, the bidirectional inverter has to be implemented in the car or at the outside of the charger. And in this case, we can simply provide the, like if
मुझे
there is
वाली
a
गाड़ी चाहिए, बेबी को वाली गाड़ी चाहिए, बेबी को वाली गाड़ी चाहिए,
बेबी को जेम्स चाहिए,
in case of just a
जेम्स
minute.
Sir, the participant is muted. You may please
Okay,
proceed.
sorry.
Thank you.
Yeah, so sorry for the disturbance. So the grid benefit is there. Why? Because as I have mentioned earlier, that whenever there is a peak load is required, either you use it. So I'll just go back to that particular. So here it is. So whenever there is a peak load required, either you don't use that load, or you give power to the grid. Correct? So you have a car and you can sell energy or you can provide energy to the grid. Hence, the peak reduces. So that is also being discussed in many institutions, and that is going to happen through vehicle to grid. So vehicle to grid gives, it is also enabling the grid to, what we have to do is we just have to reduce the peaks in the throughout the time. So either we don't use the energy, or whatever energy is required during that peak time, we provide it from the some source. So that some source can be your EV. That is why V2G is important. So similarly, we have a concept of V2H or V2B. So in case of V2H is like vehicle to home. So suppose we put inverters at home, right? When there is no electricity, we use them, and earlier lead acid batteries were being used, and now the lithium ion are being used. And so in case of V2 home, you can charge your EV from some solar plant or something outside your home, maybe at lower peak time, and then you can use that battery as a backup to your home during maybe peak hours, when you need higher requirement, or maybe during that time when the electricity is not there. Similarly, when the buildings are there, then also you can use your EV battery to, so you can read from here, peak shaving for buildings using the EV battery to supply the building during 6 p.m. peak period. This prevents the building from drawing high cost power from the utility, minimizing the monthly demand charge. And then we have to integrate the every component of the ecosystem or the system to the distributed energy resources, which is called as DER. So it means like a local source like solar PV, wind, local battery storage. So these are called as distributed energy resources. So these all comes under green energy, and then you have to use it. So cost saving example, one of the example is there. So the example is like when, as I have mentioned earlier about the concept. So this is one of the example. A commercial e-bus fleet depot requires 1.5 megawatt of power, but the local grid connection is only 1 megawatt. So the charging at 1.5 megawatt would trigger heavy penalties from the utility and require an expensive immediate infrastructure upgrade. Then smart managed cost is you are just utilizing or managing the load so that it never exceeds 1 kilowatt, 1 megawatt, and it charges the buses needed for the next route first, and shifting the remaining load to off-peak hours. And then this helps in reduce. So it is like a smart charging only, right? It reduces the 30 to 50% saving on peak demand charging, and avoid the loss of money. This is like revenue streams are also there along with the smart charging, which is like vehicle to grid. As I have mentioned, you can sell your the energy generated from the car from the grid to the grid, and then optimizing tariffs. So by time of use concept, understanding the time of use concept, you can actually save the cost, as we have discussed earlier. So this was all about the concept. So I will simply, in 2 slides, I will discuss about what we do as a company. So in EV charging, so we are a complete in-house make in India affordable and interoperable smart EV charging infrastructure company, which meets mainly the global standards. We started in 2016 in IIT Delhi, and incubated in Electropreneur Park, South Campus. And main focus is in controllers, communication cards, swapping station, software, and all that. So these are the offerings we have. We have all type of EVSEs like single phase, 3-phase, AC, DC, swapping station. These are the controllers also. So we support those companies also who want to manufacture their charger or assemble their chargers, and we have a software platform as well for optimizing all the charging sessions and all that. These are our stakeholders. So like Startup India, we are registered from there. We are there in IIT Delhi, and STPI, ISA, Electropreneur Parks, Cyber Media, Napino. So we are the 3 co-founders. One is Vikrant Kumar, second is Rupesh Kumar, and third is me, Rahul Soni. And mainly we cover end-to-end execution from design, manufacturing, deployment, and maintenance. And major milestones are like we installed first public EV charger in India, which was there in 2017, and we were recognized by Infineon, ISA, and TIE Global as a leading startup that time, 2018. And we have developed 13 plus variant of AC chargers and DC chargers. We cover from 3.3 kilowatt to 120 kilowatt of chargers. We have good collaboration with Drive, L&T EduTech, CART, IIT Delhi, BRPL, BESIL, SDMC, NDMC, like that. We have deployed swapping station, as ma'am has already told you, and 5,000 EV chargers across India. And then we have supplied 3,000 EVSE components also, as you can see in the middle of this. And we have designed one DC charger controller for BHEL R&D. And the strength is completely in-house. R&D is there. I lead the whole technical team and along with that, and we have OCPP 2.0.1 controller and ARAI NABL certified products, and we have expertise in smart load management and renewable integration. These are some of the clients which trust us. So mainly oil companies like generation companies like SJV and distribution companies like BACS, users like Bessel and HPCL, IOCL, then BHEL, then some private companies. And we have done some projects in international also, like Murata Japan, Total Energy, DIY, Cardiff University. So this was all about the session and us. So we all know that like the future grid will be managed by code only because it's all software. The role of the power and the computer engineer in e-mobility is inseparable. So thank you so much for listening and understanding. So maybe in another few minutes which we have, we can either discuss same topic from any particular slide number you want to understand, or any topic, or if you have any queries, maybe we can discuss that also.
Thank you very much, sir. Now the platform is open for all for the Q&A session. If any questions you have, you may please ask to the expert.
Yeah, if any question is there, you may ask, or otherwise, I have some time. I will discuss one or more topic from the presentation in little bit more detail.
Hello.
Hello. Yeah, hi. I think.
Am I audible, sir?
Yes, Ashutosh.
Sir, in one slide you have shown that you have developed charging management system and you give it to the local operator.
Okay. Which slide? This one?
No, sir. Here in the last slide.
This one, right?
Last slide, sir.
Yes.
Here you have in the deployment section you have said that you have designed the charging control system for the charger controller.
Yes.
And in some previous slide you have shown that the CMS system you are deploying it to the local controller.
Local controller where?
The previous slides.
This one?
Yes, sir. Yes, sir. So
Okay.
I just want to ask how many local controller can a CMS particularly operate?
Yeah, so it is again, software can handle n number of controllers. It is just the architecture of the deployment. Like for example, based on your architecture also, like we have Kubernetes. So it is, communicating, it is reducing the load on the central system or the software. Why? Because ultimately we are, if it will communicate with, 10 charge point. So now it will communicate with one hardware controller, and that can again, like with current technologies, I think numbers can be huge, like maybe in lakhs also, because Kubernetes is there. It's a scalable architecture available in Amazon Web Services and other platforms.
It is operable via wireless networks also, no, sir?
Yes, sir. Yes, sir. It is operable via wireless.
Okay. So from one site we can operate n number of sites located in different parts of the region.
Yes.
Okay. So does it manage any change in the rates or prices accordingly?
Yes.
Like in petrol pumps, we say that different petrol pumps vary for different pricing of the gas or the fuels. Same in this app for different local controllers, the prices are managed according to the state or the region, or does it vary some other concept?
Yeah. So basically, the charging session having maybe it has 15 rupees or 18 rupees. So the unit economics is you have to give the from that, it is a per unit or per kilowatt hour rate. So it is divided into 5 parts. One is electricity, which is again variable across the states, but maybe same in one particular state, right? In Delhi, it is six
Yes, sir.
rupees, 6 rupees in like including the tax, and in UP it is 8 rupees or 9 rupees. Another part is the land. So because you know that the charging station is going to install at a particular parking, so that particular parking will require a land cost also, because you are going to park your EV. So land cost can also vary. Like from the government, they have pushed that at any government place, 1 rupee per unit they have provided. Unified policy at any PSU, you can ask for 1 rupee per unit. So that is a land cost also, and that can vary. Like if you have a private property, maybe mall or some other places, so then maybe it can vary from 1 rupee to 2 rupee also. Then third is the software cost. So software cost generally is standard across India. It is like 1 rupee or 1.5 rupees is there. And then another cost is the service cost, the operational cost. Like you have to have a service engineer also, you have to have a maintenance engineer also. So that cost will also consider in that. And next
Okay.
cost is the hardware cost. Hardware meaning the charger cost, which is being installed, because you have to have a ROI on that. So these are the costs being defined in that particular session. And then after that, margin. So as you have asked, so the cost will be different for each location. So the answer is yes. It will be different based on the state, because it is going to be different for the electricity rate, and it is going to be different for the parking rate, and it is also going to be different for the charging chargers also. Like for some charger may come at 3 lakh rupees, some charger higher power may come at 6 lakh rupees. So that way also the charger cost may be different.
Okay,
And
so
that can all
mean
be controlled through the software.
That means
Sorry.
just like an electricity bill, all the additional tariffs are included in this local controller.
Yes.
Okay. Thank you, sir. And one more doubt.
Hanji, yes.
That you have deployed it for both AC and DC.
Yes.
So what type of battery or the input types you are operating for AC and DC?
So basically,
Like
in
there are
case
type
of
1 and type 2.
yes,
There are circuits for AC charging, and for DC, as far as I know, there is CHAdeMO as well as CMS is also for DC.
yes, CCS, not CMS, it's CCS.
CCS,
Yeah.
sorry, CCS and
Yeah.
CHAdeMO.
Yeah, so CHAdeMO is the cars.
Is
CHAdeMO
it
is mainly
operable in India?
No, it's not very much operable, because it is coming,
Okay.
it's a standard from Japan. So Japanese car like Nissan Leaf and all that are not coming in India as of now. Majorly, initially, when we started in 2017, we worked on GB/T, which is like DC001 protocol, which you can see in this particular slide, right? It is a
Yes, sir.
15 kilowatt charger, and it is based on the Chinese standard. Later, because it has a lower voltage, 190 or 120 volt or 100 volt, but later all the car manufacturers, they adopted, and the Indian government also adopted CCS type 2, which is an European standard. So based on that, we have to switch from GB/T or DC001 to European standard, which is CCS2. So now
Type
we
2.
have both, yes, type 2. So in case of type 2 also, we have AC chargers and we have DC chargers.
Okay, sir. Thank you so much, sir.
Thank you.
Any other query from the participants?
Good evening, ma'am. I have a doubt. Sir?
Yes, please.
Sir, in the last slide, you have mentioned about revenue streams. In that, I need a clarification, sir, because you have told about selling with flexibility. In that demand response service, I'm doing my project in demand response side for EV charging station. And in so many papers I have gone through that, there is someone called demand response aggregator. So what does the aggregator mean, sir? Either a charging station or else, the demand response aggregator is between the utility and the grid. And what is the purpose?
No, so it is between the charging station and the grid, or charging station and the utility. That is the demand side aggregator is there. So because they know how much supply we have, and they know how much demand is there. So they have to, make a balance between the EV charging stations or maybe some other loads and the distribution companies also. So those are like demand side aggregators. There are no not many aggregators are there in India as of now, because this is a very this is a task which Discom might take up in India. But yes, once this popularity will increase, so in case as we have a Western or the cases in abroad, so similar will come into this in India also, where the software or the company will mitigate or will meet the demand of the charging station and negotiate with the distribution company, maybe with the at a particular tariff rate, or it can sign an agreement also between the distributor and the user. Like for example, we have a charging station for in Delhi we have Delhi Metro, right? So whenever Delhi Metro construction happens, so they have an agreement with the distributor that whatever happens at this particular time, we need the full capacity, correct? So similarly, that kind of job for a charging station will also be there, which will be mitigated by the aggregator, which you have just mentioned.
So the aggregator will be a third party, or the person, I mean, they are incorporated with the charging station or the distribution system.
Right. So it will between distribution company and the charging company, because it is going to be a software only, because everything they have online. So software being run by a company only. Like as I have mentioned about Paytm or Make My Trip. So these are also software, and we have different software, but Paytm is also a company, right? So company is being run through the software only. So as you can see from here also, so distribution I have not mentioned in that would be very complex sort of block diagram. So this is this charge point operator and electricity supply. There will be another category will come, that is a load side management aggregator. It will be a software only for sure.
Okay, sure. Thank you, sir.
Thanks.
Hello. May I, sir?
Yes.
Sir, I wanted to know, I've been reading a lot about ultra fast charging, where 350 kW charging happens. And where the charging time can be reduced to 15 to 20 minutes. So what is the feasibility of it when it comes to India? Like, is it because we have a system wherein the charging happens at 400 volt architecture of the vehicle, so we may have to switch to 800 volt system. So do you think it's feasible enough to like have this kind of system in India?
Yeah, so it is already 180 kilowatt is already there in cars, right? So that is a maximum for Mahindra BE and for Audi and all that. So it is already there. For when we are talking about 350 kilowatt, so for the buses and the trucks, it is going to be implemented very fast. And in case of buses, currently what is happening is there are two batteries being charged at the same time with the help of 120 kilowatt, which means we are supplying 240 kilowatt at the same time with one charger to one vehicles. Although that is technically being used for 120. So similar way, complete 360 kilowatt. Even in India, there is a company called as Exponent. You can read about it. They have made a ultra fast charging of 1 megawatt, not only 350 kilowatt, of 1 megawatt, where they have a liquid cooling facility is also there in through the charging gun. So they have two different probes for cooling happening through the battery and through the charging also while charging. So yes, it is definitely going to come, and voltage will not, for 800 volt, it will come in the trucks and buses. For cars, I believe the current architecture will remain there. Yeah, but in future, because it is very unpredictable kind of scenario in India, as like we have been working since 2017, so we have changed a lot of transition in this particular domain. So yes, it can happen for 800 volt also, but preferable for cars will be 400 volt, 480 volt only. For trucks and buses, it will for mainly for trucks, it will come for 800 and higher voltage. Even battery storage system is not at 800 volt in India right now.
Yes, sir. Thank you so much.
Thank you.
Any other query from the participants? I think that session was too much interactive, sir, and you have shared your expertise with us. So, with formal conclusion of the session, I would like to thank you specially for sharing your deep expertise with all the participants, which has truly enlightened us on the future of charging infrastructure, smart energy management, and the evolving landscape of the electric mobility. The practical insights, industry perspectives, and the real world examples from your presentation you have shared have immensely benefited all the participants. And we sincerely appreciate the time that you took from your busy schedule, sir, to guide us today. And your contribution has added the great value to our program as well. So I'm very thankful on behalf of Shri Vishwakarma Skill University, sir, to you for sharing your expertise with us. So I would request all the participants to please switch on their webcam so that we can have a group photograph with sir. Rahulji, please confirm if it's done. Okay, I've taken the snapshot. Thank you everyone, and we will be again meeting tomorrow at 6 p.m. And I would like to inform that 6 p.m. tomorrow the session will be taken by Mr. Ramanna, and he's from the MathWorks. Will be taking the hands-on session for the e-mobility solutions. So thank you very much for being connected, and we will meet again tomorrow on the 4th day of FDP. Thank you everyone. Thank you very much, sir. Thank you, sir.
Yeah, thank you everyone. Good night. Thank you, ma'am.
Thank you, sir. Good night, sir.